Welcome to this problem walkthrough. In this session, we'll be tackling LeetCode problem number 976, titled Largest Perimeter Triangle. This problem challenges us to identify the largest perimeter of a triangle that can be formed using an array of stick lengths. Let's dive in and explore the solution approaches step by step. In this problem, we need to determine the largest perimeter of a triangle that can be formed using 3 stick lengths chosen from an array nums. If no valid triangle can be formed, we simply return 0. For a triangle to be valid, it must satisfy the triangle inequality, which states that the sum of the lengths of any two sides must be greater than the length of the third side. The input is an integer array nums where its length is at least 2 and at most 10,000, and each element is a positive integer up to 1 million. The output is an integer that represents the largest possible perimeter of a valid triangle, or 0 if no triangle can be formed. Let's consider an example to better understand the problem. Suppose the input array is nums equals 2, 1, 2. After sorting the array, we get 1, 2, 2. To check if a triangle can be formed, we verify the triangle inequality conditions: 1 plus 2 greater than 2, 1 plus 2 greater than 2, and 2 plus 2 greater than 1. Since all these conditions are satisfied, the 3 lengths can form a valid triangle. The perimeter of this triangle is calculated as 1 plus 2 plus 2, which equals 5. This is the largest possible perimeter we can achieve with the given lengths, so the output is 5. Now, let's look at another example where no valid triangle can be formed. For the input nums equals 1, 2, 1, we start by sorting the array, which gives 1, 1, 2. Checking the triangle inequality, we find that 1 plus 1 is not greater than 2. This means that these 3 lengths cannot form a valid triangle. As a result, the output is 0 since no triangle can be formed. Now, let's analyze a more complex example where we have more lengths in the input array. In the example nums equals 3, 2, 3, 4, we first sort the array to get 2, 3, 3, 4. To find the largest perimeter, we start with the 3 largest sides, 3, 3, and 4. Checking the triangle inequality, we see that 3 plus 3 greater than 4, 3 plus 4 greater than 3, and 3 plus 4 greater than 3, so these lengths can form a valid triangle. The perimeter of this triangle is 3 plus 3 plus 4, which equals 10. This is the largest possible perimeter with the given lengths, so the output is 10. Additionally, we must ensure the solution handles constraints like input sizes up to 10,000 in edge cases, such as arrays with just 3 elements, duplicates, or very large values. To solve the problem of finding the largest perimeter triangle, several approaches can be considered. The most straightforward is the brute force approach. Here, the intuition is simple: we examine all possible combinations of 3 stick lengths from the array and check if they can form a valid triangle. For a valid triangle, the sum of any two sides must be greater than the third side. Once we identify a valid combination, we calculate its perimeter and keep track of the maximum perimeter encountered. The steps for this approach involve iterating over all triplets, verifying the triangle inequality conditions, and updating the maximum perimeter when valid combinations are found. However, this method has a time complexity of n cubed, due to the 3 nested loops required for generating all triplets. While it's easy to implement, it becomes computationally expensive and inefficient for large inputs, making it unsuitable for arrays of size up to 10 to the power of 4. To overcome these limitations, we consider an optimized approach that leverages sorting to reduce computational overhead. By sorting the array in descending order, we can focus on the largest side lengths first, which are most likely to yield the largest perimeter. This method ensures that if a valid triangle cannot be formed with the largest 3 sides, it's impossible to form one with smaller side lengths, significantly reducing the number of checks required. The optimized approach begins by sorting the array in descending order. This ensures that the largest possible side lengths are considered first, making it easier to identify the largest valid triangle. Once the array is sorted, we iterate through it, checking consecutive triplets to see if they satisfy the triangle inequality condition. Specifically, for any triplet, nums I plus 1, nums I plus 2, we verify whether the largest side, nums I, is less than the sum of the other two sides, nums I plus 1, plus nums I plus 2. If this condition is met, the triplet forms a valid triangle, and we return its perimeter as the sum of the 3 sides. If no valid triangle is found after examining all triplets, we return 0, indicating that no triangle can be formed. This approach is much more efficient than brute force. Sorting the array takes O, n log n, and the single pass to check triplets takes O, n, resulting in an overall time complexity of O, n log n. The space complexity is O, 1, as the sorting can be done in place. While this approach is efficient, a trade-off is the upfront cost of sorting the array. An alternative strategy could involve using a priority queue or max heap to dynamically find the 3 largest elements. However, maintaining the heap structure adds overhead, making it less practical than sorting for this specific problem. The heap-based approach, while an alternative, comes with its own set of trade-offs. Its time complexity is O, n log k, where k is 3 for extracting the top 3 elements, and it requires O, k, additional space for the heap. This added complexity makes it less efficient overall compared to the sorting-based approach. For this problem, the optimized approach using sorting was chosen because it strikes the best balance between simplicity and efficiency. Sorting the array ensures that we can quickly identify the largest valid triangle without unnecessary computations. This approach scales well for larger inputs and has a final time complexity of O, n log n, which is optimal for this problem. Additionally, it uses O1 space as the sorting can be performed in place. The brute force method was discarded due to its inefficiency for large inputs, and the heap-based approach was set aside because its complexity outweighs its benefits. By focusing on the sorted array, we ensure correctness, minimize computational overhead, and maintain a straightforward implementation. This makes the sorting-based method the ideal solution to efficiently solve the problem of finding the largest perimeter triangle. To solve the problem of determining if any 3 stick lengths can form a valid triangle, we first need to understand the triangle inequality conditions. A triangle is valid if the sum of any 2 sides is greater than the third side. For 3 stick lengths, A, B, and C, this means that A plus B must be greater than C, A plus C must be greater than B, and B plus C must be greater than A. These conditions ensure that the sides can physically connect to form a closed shape. One way to approach this problem is through a brute force method. Here, we would generate all possible combinations of 3 stick lengths from the array and test each combination against these conditions. Using 3 nested loops, we can iterate over all unique combinations, ensuring that the indices follow the order I less than j less than k to avoid duplicates. However, as we'll see, this approach is computationally expensive when the array is large. For example, let's take an array of stick lengths, 2, 3, 4. The only possible combination of 3 sticks is 2, 3, 4. For this combination, we check the triangle inequality conditions. Specifically, we confirm that 2 plus 3 is greater than 4, 2 plus 4 is greater than 3, and 3 plus 4 is greater than 2. Since all conditions are satisfied, this combination forms a valid triangle. The brute force approach would return true in this case. However, as mentioned earlier, this method involves a lot of unnecessary computation because it checks all possible triplets, even when many of them can be eliminated early. To improve efficiency, we turn to an optimized approach that combines sorting with a greedy strategy. By first sorting the array, we can ensure that the largest value in any triplet is always the last element. This allows us to simplify the triangle inequality check significantly, as we only need to verify one condition for each triplet, whether the sum of the 2 smaller sides is greater than the largest side. After sorting the array, we can iterate through the elements using a single loop. Starting from the third element, we consider each triplet formed by the current element and the 2 preceding elements. For the triplet at indices k2, k1, and k, we check if the sum of the 2 smaller sides, a, k2, and a, k1, is greater than the largest side, a, k. If this condition is met, the triplet forms a valid triangle, and we can immediately return true. If no valid triangle is found after iterating through all possible triplets, we return false. When analyzing the time complexity, the brute force approach is O, n cubed, due to the 3 nested loops over the array of n elements. In contrast, the optimized approach involves sorting the array, which is O, n log n, followed by a single pass through the array, which is O, n. This results in an overall time complexity of O, n log n. The key insight here is that sorting the array reduces the complexity of the triangle condition checks, allowing us to focus on the most critical inequality. Additionally, the greedy nature of this approach enables early termination as soon as a valid triangle is found, further improving efficiency. The optimized approach can be implemented in Python with the following code. First, we define a function to check for valid triangles. Inside the function, we sort the input array, which ensures that the largest value in any triplet is always the third element. Then, we iterate through the array starting from the third element. For each triplet formed by the current element and the two preceding elements, we check the triangle condition, whether the sum of the two smaller sides is greater than the largest side. If this condition is met, we return true immediately, indicating that we've found a valid triangle. If the loop completes without finding any valid triangles, we return false. The key operations here include sorting the array to simplify the checks, using a single loop instead of nested loops, and leveraging early termination to improve efficiency. This approach also handles common edge cases, such as arrays with fewer than 3 elements, all 0 or negative values, and large numbers. By combining sorting with a greedy strategy, this solution achieves both simplicity and efficiency. This Python implementation solves LeetCode problem number 976, largest perimeter triangle. The goal is to determine the largest possible perimeter of a triangle that can be formed from an array of integers representing stick lengths, or return 0 if no triangle can be formed. The algorithm begins by sorting the input array nums in descending order. This ensures that the largest possible sides are considered first, which is critical for maximizing the perimeter. Next, the code iterates through the sorted list using a for loop. At each step, it checks whether 3 consecutive sides, nums I plus 1, nums I plus 2, satisfy the triangle inequality condition, nums I plus 1, plus nums I plus 2. If this condition is met, the sides can form a valid triangle, and the perimeter is returned as their sum, nums I plus 1, plus nums I plus 2. If the loop completes without finding any valid triangle, the function returns 0, indicating that no valid triangle can be formed with the given sides. This solution is efficient, with a time complexity of O n log n due to the sorting step, and O n for the loop. This makes it suitable for large input sizes within the problem's constraints. The code handles edge cases, such as arrays with fewer than 3 elements, by returning 0 immediately since a triangle cannot be formed with fewer than 3 sides. Overall, this implementation is concise, efficient, and directly addresses the problem requirements. This is the Java implementation of LeetCode problem number 976, largest perimeter triangle. The logic mirrors the provided Python solution. The input array is sorted in ascending order, and we iterate from the largest side to check if 3 consecutive sides can form a triangle based on the triangle inequality rule. The key differences include explicit type declarations for variables and the use of Java's arrays.sort for sorting. If no valid triangle can be formed, the method returns 0. To solve the problem of finding the largest perimeter triangle, we start by understanding the input and the requirements. The input is an array of integers, nums, where each integer represents the length of a stick. Our goal is to use 3 of these lengths to form a triangle with the largest possible perimeter. If it's not possible to form any triangle, we simply return 0. Let's look at the first example where the input array is 2, 1, 2. The first step is to sort the array in descending order, which gives us 2, 2, 1. Sorting is important because it allows us to check for the largest possible triangle first. Now, we iterate through the array, starting from the largest number, and check the triangle condition. The sum of the 2 smaller sides must be greater than the largest side. For this case, at index 0, we have 2, 2 plus 1, which is true, so these 3 sides, 2, 2, 1, can form a valid triangle. The perimeter of this triangle is 2 plus 2 plus 1 equals 5, and that's our result for this example. Now, let's consider another example with the input 1, 2, 1. Again, the first step is to sort the array in descending order, resulting in 2, 1, 1. Once sorted, we start iterating through the array to check the triangle condition. At index 0, we have 2, 1 plus 1, which evaluates to false. This means that these 3 sides cannot form a valid triangle. Since there are no other combinations to check, we conclude that it's not possible to form any triangle with this input. As a result, we return 0. For the third example, the input array is 3, 6, 2, 3. Following the same process, we first sort the array in descending order, which gives us 6, 3, 3, 2. Next, we start iterating to check for the triangle condition. At index 0, we have 6 3 plus 3, which is false, so we move to the next index. At index 1, we check 3 3 plus 2, which is true. This means the sides, 3, 3, 2, can form a valid triangle. The perimeter of this triangle is 3 plus 3 plus 2 equals 8. Since this is the largest perimeter we can achieve with this input, that becomes our result for this example. To summarize the key insights, sorting the array in descending order is an important step because it ensures that we check for the largest possible triangle first, which helps maximize the perimeter. The triangle inequality condition, a less than b plus c, is what determines if three sides can form a valid triangle. If no valid triangle is found during the iteration, we return 0. The overall time complexity of this approach is efficient, with O, n log n, for sorting the array and O, n, for the iteration, making it well suited for this problem. The time complexity of the solution can be broken down into two main components. First, we sort the input array nums in descending order using Python's built-in sort, reverse equals true, function. Sorting an array of size n takes O, n log n, time, which is the most computationally expensive step. After sorting, we iterate through the array using a for loop, checking groups of 3 consecutive sides to determine if they can form a valid triangle. Since the loop runs a linear number of times, specifically in 2 iterations, this step contributes O, n, to the total complexity. When we combine these, the sorting step dominates, making the overall time complexity of the solution O, n log n. Now, let's examine the space complexity of the solution. The input array nums itself requires O, n, space, as it holds all the elements of the input. For sorting, Python's timsort algorithm is used, which is an in-place sorting method. While timsort modifies the input array directly, it does require a small amount of additional space, specifically O, log n, for maintaining the recursion stack during the sorting process. Besides this, the solution uses a few variables for the loop and condition checks, such as I and individual elements of nums. These require constant space, or O1. Therefore, the overall space complexity is dominated by the input storage, resulting in a total of O, n. We can also analyze the best, average, and worst-case scenarios for this algorithm. In the best case, a valid triangle is found in the very first iteration of the loop. Even though the loop terminates early, the sorting step still dominates, so the overall time complexity remains O, n log n. On average, the loop will iterate through about half the array before finding a valid triangle or determining that no valid triangle exists. Regardless, the sorting step ensures that the average time complexity is also O, n log n. In the worst case, no valid triangle can be formed, meaning the loop runs for all n 2 iterations. Despite this, the sorting step still dictates the overall complexity, which remains O, n log n. Finally, let's compare this solution to a brute force approach and verify its big O complexity mathematically. A naive solution would involve generating all possible combinations of 3 sides from the array, checking the triangle inequality for each, and computing the perimeter. This approach requires evaluating c, n, 3 combinations, which leads to a time complexity of O, n cubed. By sorting the array first, our solution reduces the problem to a single linear scan, achieving a vastly improved time complexity of O, n log n. Mathematically, the sorting step accounts for O, n log n, while the linear scan adds O, n. Since O, n log n, dominates, the total time complexity is O, n log n. Space complexity is determined by the input storage O, n, and the minimal auxiliary space O, log n, resulting in a final space complexity of O, n. When working on this problem, there are several common mistakes to watch out for. First, not sorting the array is a frequent error. Sorting ensures that the largest side, or C, is always the last element in the triplet, which simplifies the triangle condition check to just A plus B greater than C. Without sorting, you might end up checking unnecessary combinations. Next, you need to handle edge cases carefully. Arrays with fewer than 3 elements, like 1, 2, or an empty array, cannot form a triangle, so explicitly checking for these cases will prevent runtime errors. Another pitfall is using a brute force approach with 3 nested loops, which results in an O, n cubed, time complexity. While it might work for small arrays, it becomes inefficient as the input size grows. Instead, optimized techniques like sorting and two-pointer methods offer better performance. Additionally, some implementations unnecessarily check all three triangle inequalities: a plus b greater than c, a plus c greater than b, and b plus c greater than a, which is redundant when the array is sorted. Simplifying to just a plus b greater than c eliminates these extra checks. Lastly, if you're dealing with floating point values, be cautious of precision errors. Small inaccuracies in comparisons can lead to incorrect results, so consider using rounding or a small epsilon value to ensure reliable calculations. In interviews, this problem is often used to evaluate your problem-solving and optimization skills. Recognizing the triangle inequality pattern and understanding that sorting the array is a critical first step are key points interviewers look for. They also value your ability to discuss efficiency trade-offs. For example, while a brute force approach has a time complexity of O(n cubed), using sorting combined with a two-pointer strategy reduces this to O(n squared), demonstrating a clear grasp of optimization. Additionally, being proactive about edge cases such as empty arrays, arrays with fewer than 3 elements, or inputs with duplicate values shows your attention to detail and thoroughness. Some interviewers may even explore real-world applications of this problem, like triangulation in computer graphics or geometric algorithms. Being able to connect your solution to practical scenarios adds depth to your explanation and highlights your ability to think beyond the immediate coding challenge. This problem is closely related to several other problems on LeetCode that you might encounter. For instance, LeetCode 611, valid triangle number, asks you to find the number of valid triangles that can be formed from an array. This overlaps conceptually with the triangle inequality and optimized approaches. Another example is LeetCode 15, 3sum, which requires finding unique triplets in an array that sum to 0. Here, the three-pointer or two-pointer approaches play a central role, just as they do in this problem. Similarly, LeetCode 16, 3sum closest, challenges you to find a triplet whose sum is closest to a target value, again requiring careful optimization strategies. Lastly, LeetCode 18, 4sum, generalizes the 3sum problem to 4 numbers, demanding even more efficient techniques like sorting and two-pointer methods. Exploring these related problems can deepen your understanding and prepare you for variations of the same pattern. Regarding approaches, while brute force implementations with O(n cubed) complexity are straightforward, they are inefficient for larger arrays. Optimized sorting combined with two pointers is significantly faster and more practical, though it does require a solid grasp of the two-pointer logic. Another alternative to consider is the counting-based approach, which also achieves an O(n squared) complexity under certain constraints. This technique leverages frequency counts, often implemented using a hash map, to optimize the search for valid side lengths. While this approach is not universally applicable, it can be faster in specific scenarios where the input data supports it. The trade-off here is that it's more specialized and may require additional preprocessing, but for the right problem constraints, it can deliver excellent performance. Understanding when and how to apply this method demonstrates flexibility in your problem-solving toolkit, which can be especially valuable in interviews or real-world problem solving. Great job! Here's a quick recap of what we covered. We solved the problem by sorting the stick lengths and leveraging the triangle inequality to find the largest perimeter. Sorting turned out to be the key to simplifying the solution. Remember, mastering concepts like this is essential for tackling more advanced problems. Thanks for joining, and see you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!